A large piece of poster board paper is 40 inches wide and 55 inches long. Let's just start with that, actually. So the length is 55 and the width is 40, okay? A square is going to be cut out of each corner, and I don't know how much that square is going to be in length, but I know it's like X by X, okay? And then we're going to take the remaining paper, we're going to fold it into a rectangular box with no lid, so you can keep your family of miniature hairless trolls in it. I don't know, made it up. What value of X will maximize? That sounds like optimization to me. The volume of the box, and what is that volume? So we need to answer two questions. In this case, we need to find the X value and the volume that corresponds to it, so here we go. I want to demonstrate what's really going on here. I'm going to zoom out just a little bit. There we go. We're going to get a piece of paper, and we're going to cut a square out of each corner, and I don't know how big that square is going to be. So we cut a square out, and we cut the same square out of here. Now I'm eyeballing it. And I'm going to cut a square out at this one. And I'm going to cut a square out of this one. And when I do, I have this right here. There we go. Pardon my scrap paper on the back side. And we have a little box. And this box is going to have a volume. Now, it doesn't have a lid. We're just going to keep the family of miniature hairless trolls in there. And we're going to put them in, and they're going to be able to jump out, but whatever. So this is our box. Okay, back to the original problem. This was 40, right? They said so. This whole distance across here was 40. Well, if that's 40 and this is X and this is X, then this distance right here is going to come in pretty handy. 40 minus X, that's going to be 40 minus 2X. Okay? Now, keeping in mind, same situation here. This was X and this was X. And in our original problem, the length, which I put sideways, was 55. So 55 minus X minus X. This distance right here is 55 minus 2X's. And then, just be real practical, this is X. If I fold it up, the height of this box is X. Let's take that thought and run with it. Zoom back in. Whoops. Let's try this again. There we go. All right, so switching to red. This distance across here, we just figured it out. It is 40 minus 2X. And this distance across here is 55 minus 2X. And then this distance right here is just X, okay? So we're dealing with the volume. Let me straighten this up. We're dealing with the volume of this box. The volume of this box is going to be basically length times width times height, but not length and width, but like the new length and the new width and the new height. So it's 40 minus 2X for the width, 55 minus 2X for the length, and the height is X. So the volume of this box is the one thing they're asking me about. Okay, very first problem, they gave us something we knew and asked for something we didn't know. This time they really didn't tell us anything that we knew, but we did have enough information because we're really just dealing with one variable. So the volume is going to be length times width times height. But the length of the box, well, the width of the box is 40 minus 2X. Length of the box is 55 minus 2X. And the height of the box is X. Feel free to distribute as much as you like, but they are asking for a maximum. So why don't we just graph it and find it, which is what I'm about to do. So here goes. 40 minus 2X, 55 minus 2X, and X. So y equals, parentheses, 40 minus 2X, 55 minus 2X, and X. Okay, now I'm going to go to a standard window and we're looking at it and we're like, oh, what? And again, you can say, oh, I got an x-intercept. Oh, let me go. Got an x-intercept and now there's an x-intercept. Irrelevant. Don't need x-intercepts right now. Just saying. What I do want to do is find a maximum, and that maximum is somewhere. So let's start zooming around. Now I'm going to do a thing where I pinch the screen, and I'm going to drag this down. Oh, there we go. I typed it wrong. Good learning opportunity. There we go. Let's fix this thing. There we go. Much better. Okay, it's going up. I thought that looked wrong. It looked like a It looked like something that wasn't right. I'm going to pinch this. There we go. We have a maximum. Now, we have an absolute maximum of infinity, but let's be real honest. If we're going to have a box with an infinite capacity, then we're going to have an x value that is infinite. Well, you can't cut infinity off of this box, right? You can't do it, right? So this is what we're dealing with, and that is the answer, staring this in the face. So the output of this function that I finally typed correctly is the y value. That's the maximum value of the box, maximum volume of the box. And this is the x value that gives us that. So I'm going to write those numbers down. I'm going to sketch a quick graph of it too. So x equals 7.62595. I'm going crazy with my decimals here. And then that maximum volume is 7,501.5704. I usually don't use that many decimal places, but you know, after I made that other mistake, I figured I'd fix it somehow. And what I'm really doing here is finding a maximum. I found that coordinate right there, and they asked for both the x value and the output